today we are finding antiderivatives of polynomial type functions. So first off, let's talk about what a polynomial type function is. A polynomial is separate terms written out that have variables with whole number positive exponents. So like x squared, x cubed, x to the first power, constants are good. What is not an actual polynomial is like x to the 1/2 power or x to the -2. However, if we can write a function so that it is written out like a polynomial, even if the exponents are negative or fractions or something, then we can still use like the power rule when taking derivatives. So we can use the opposite of the power rule today for polynomial type functions to take what is called an antiderivative. So first off, let's explain to someone how to find the derivative of a polynomial type function. So let's say we had, let's go with f of x, and that's going to equal 5x to the third power plus 4x squared minus 7. If we were going to take that derivative, we would start out by writing f prime of x equals to show that we had taken a derivative, right? The prime to show that that's the derivative of f. And then we would use the power rule. The power rule has two steps. Step 1 is take the exponent and multiply it times the coefficient. Okay, so that 3 multiplies times the 5 to get 15. And then we need a new exponent. We take the x and we decrease that exponent of 3 by 1 to get a 2. So step 2 was exponent minus 1 gets us the new exponent. And we can repeat that for 4x squared, so plus 8x to the first power. Then that minus 7, I'm going to make that a minus 7x plus 4. How about that? So we've got a linear term and a constant term. So switch that up. Negative 7x, that would be to the first power. So 1 times negative 7 is negative 7. And then x becomes x to the 0 power. X to the 0 power, or anything to the 0 power, is 1. So that guy just kind of disappears. Moving over here, we have a 4, which is really a 4x to the 0 power. So when we multiply that exponent of 0 times 4, we get 0, x to the -1. But really, since we have a 0, that whole term, which was a constant term, will disappear. In the next box or area right here, it says to find an antiderivative, you would do the opposite of each one of those operations in the reverse order. So we're doing inverse operations. We're going to start with step 2, which was exponent minus 1. So it's going to be something to do with that exponent. I'm going to rewrite our f prime of x, which was 15x squared plus 8x minus 7. So same thing we just had. But now our goal is to get f of x. So we're not taking a derivative, we're taking an antiderivative, the opposite. Okay, so since our last thing here was exponent minus 1, it seems like our first step should be exponent plus 1. That's how we get that 3. Okay. Then to get the 15 up here, we multiplied the 3 exponent times the 5 coefficient. There wasn't a 3 exponent to begin with, and getting 15 divided by 2 would give us 7.5. That's not 5. So it looks like we're going to have to do coefficient divided by the new exponent to get our new coefficient. So 15 divided by 3 is 5. Coefficient divided by new exponent. So you'll see as I do these, I usually write down the x first and then increase the exponent and then figure out the coefficient. So I know it looks kind of backwards and mismatched and whatever, but you need to know what the new exponent is before you can divide. All right, let's move on to the next term. Plus x to the, it was a 1, now it's a 2 for the exponent. And then 8 divided by 2 is 4. Bring down the minus, give us an x, right? Because there was no x, which means that there needs to be an x to the first power. And then 7 divided by 1 is 7. or negative 7 divided by 1 is negative 7, if you want to do it that way. We run into a problem, though, and it's the fact that we can't get that 4 back. There should be a little plus 4 right here. We know that. But 4's derivative was 0. So I guess technically there's like a little plus 0 that's just hanging out over here that we just don't really know about. And 0 is the derivative of any constant. So since 0 is the derivative of any constant, we don't know what its antiderivative is for this particular problem. Okay, technically we know it's a plus 4, but for any problem in general, we don't know what that's supposed to be. So we're going to do kind of a little general version of a constant and put plus c at the end. Okay, that is a calculus thing, not just a Miss Campbell thing. Anybody uses plus c at the end of an antiderivative. All right. The antiderivative of a function f of x is denoted by this notation right here. I'm going to read this to you. This symbol right here, this S-looking thing, is called an integral sign. Then we have f of x, the thing that we are taking the antiderivative of, and then the little dx at the end. We've seen dx all over the place. The d over dx bit, that means take a derivative with respect to x. So this reads as take the integral or antiderivative of this function f of x with respect to x. So do the opposite of taking the derivative of f of x. Okay. Sometimes it's easier to, instead of thinking of all of like your steps of your power rule, your opposite anti-power rule really, instead of thinking about that, you can think of what is 15x squared the derivative of? What is this the derivative of? And then you can figure out what that term is. That's especially helpful to me when I've got a constant. A constant is the derivative of a linear term, so we've got to have that x there. 0 is the derivative of a constant. So sometimes that wording can help you out. Okay, this enables us, using this notation, what is this the derivative of, enables us to find f if we are given the function f prime or even f double prime. So we can start with either of these guys and figure out what the function f is, except of course for that constant. If f had a constant, f prime would have a 0. Okay, so we have to put plus c at the end of every antiderivative. Okay, let's find some following antiderivatives. We've got 4 examples here, all of different shapes and sizes. The first one is already set up really well for us because it looks exactly like a polynomial. In fact, it is a polynomial because everything's got positive or, well, non-negative whole number exponents. Okay, let's use that power rule, anti-power rule. X was to the second power, so now it's to the third power. And then 3 divided by 3 is an invisible 1. You can write that 1 if you like, but you definitely don't have to. Plus x to the, it was a 1 exponent, now it's a 2. And then 2 divided by 2 is another invisible 1 in front. Plus 3, just a constant, would be the derivative of 3x. Okay, so those are our 3 terms, and then of course you put a plus c at the end. These problems are super, super easy to double check without writing anything else down. So I recommend, especially as you're practicing them, and anytime you have a quiz or a test or anything, you definitely take your derivatives. X cubed has a derivative of 3x squared. Check. X squared's derivative is 2x. 3x's derivative is 3. And we've got our plus c, whose derivative is 0. Moving on. we've got a fraction this time. There's nothing wrong with this fraction, but we don't have like a quotient rule or a product rule that we can use for antiderivatives, unless your problem is already set up like beautifully and it looks like the quotient rule. Now this doesn't. So we are going to do some simplifying. You have a couple of options. You could take that x, make it to the -1 power, bring it up to the top, and distribute that times all of these terms. That is absolutely an option. But off to the side, I'm going to do a different method, and that's going to be to rewrite, this is going to be side work. I'm going to take that x to the third plus 2x minus 4 and split it up, all of these little guys over x. Okay, if there's only one term in a denominator, you can split up all of your numerator terms and give them all the exact same denominator. Okay, so this goes back to like your 4th grade math of common denominators. If all of your fractions have common denominators, you're allowed to add and subtract their numerators, and you keep the denominator. Of course, these are x's, so this isn't like exactly 4th grade math. It's definitely high school, but that's the idea behind it. Okay, and then from here, you can do some simplifying. X cubed divided by x is x squared, plus 2x divided by x is 2. And then -4 over x, you can write that several different ways. Let's start by writing it as -4x to the -1. And this is the exact same thing that you would have gotten if you had brought the x to the -1 up to the top and distributed. So I'm going to rewrite this in the parentheses because we have not taken a derivative or an antiderivative or anything. We've just rewritten the parentheses. So this equals the integral of x squared plus 2 minus 4 x to the -1. Something weird's going to happen, so I'm putting that part in parentheses or in a pencil. So spoiler alert, something's not going to be right. It's going to be weird with this guy. Okay, let's take an antiderivative. As we take derivatives, we do it one term at a time. Same thing with antiderivatives. Don't get so focused on the whole problem that you can't do the little pieces of it. Okay, antiderivative of x squared. So we have x to the, increase the exponent by 1 to get a 3. And then the original coefficient of 1, you're going to do 1 divided by that 3 and get 1/3. Plus 2 is the derivative of 2x. Okay, this guy. If we increase that exponent by 1, we would get x to the 0 power. And then we would take the coefficient, which is -4, and divide it by 0. So we've got some issues here. First issue is that we've got x to the 0 power, which really would disappear. And if x to the 0 power disappears, that would make this guy a constant. And we know that the derivative of a constant would be 0. So this term shouldn't even exist. Okay, that was one issue. A second issue is that we cannot divide by 0. -4 divided by 0 is undefined. So this method does not work for x to the -1 power. Okay, I'm going to do some erasing. So we've got like some red flags here. I'm going to erase a little bit, just that piece. And I'm going to switch it out for a 1 over x instead of x to the -1. So it's -4 times 1 over x. The answer for that is going to be -4 times, and then we have to think about this. What is 1 over x the derivative of? It was something special. 1 over x is the derivative of the natural log of x. Okay, so I showed you that not because I just wanted to waste our time. What I wanted to show you is that when you accidentally do that and you get that 0 exponent, you know that something is wrong. You didn't totally mess up everything, and you can fix it. So just rewrite as a 1 over x instead of x to the -1. That is the only one of these polynomial type function terms that is really an issue. Okay, Of course, we got to put our plus c at the end because the derivative of c is 0, and there's always an invisible plus 0 at the end. Let's keep going. On this next guy, we have two binomials that are multiplied together. So we can do a rewrite of this problem by distributing and combining like terms. So this is going to equal the integral of x squared, let's see, plus 2x squared minus 3x plus 4x, so plus x minus 6 dx. Okay. This looks a little bit different writing-wise than this one did. Notice this one had parentheses around the entire polynomial. It just kind of further underscores the fact that you're taking the integral of that whole polynomial, so I'm going to stick parentheses around mine as well. All right, we're taking the integral of the whole thing, not just of one term. Okay, let's take that antiderivative one step at a time. X will now be to the third power. And then 2 divided by 3, we'll just put a 2/3 fraction in front. Plus x is now squared. 1 divided by 2 is 1/2. Constant, so we've got negative 6x. And then plus c for our unknown constant that we know is supposed to be there, we just don't know what it is. This is called the general form if you've got just like plus c at the end. In future problems, we will be able to figure out what c is, but we have to be given some extra information for it. All right, let's do a rewrite of this guy as well. We've got that this integral equals the integral of 2x to the negative 1/2 dx. This problem did not utilize parentheses because there's only one term. You can use parentheses around one term if you want to. Your choice. When you take the antiderivative, take that integral, the integral sign and the dx get used. So this tells you to take the action of antiderivative. So when you have done the antiderivative, that is now gone. Kind of like when you take a square root of 9, you just write 3. You don't write the square root of 3. It goes away. All right, increase that exponent by 1. Negative 1/2 plus 1, this is side work over here, is the same thing as negative 1/2 plus 2/2, which is positive 1/2. Okay, so that's now positive 1/2. Now we're going to take this 2 and divide it by the new exponent of 1/2. Okay, a little bit more side work. 2 divided by 1/2. If you divide fractions, that's the same thing as multiplying by the reciprocal of that second fraction. So when you're dividing fractions, you flip the second fraction and multiply. 2 times 2/1 is the same thing as 2 times 2, which is 4. Okay, stick a little plus c on the end and we are done. Double check to make sure that you get the right stuff, because these fraction guys are a little finicky, you know? 1/2 times 4 is 2, and then 1/2 minus 1 is negative 1/2. We're good. Okay, next page. Sines and cosines. Okay, we've done sines and cosines for derivatives. I'm going to have us draw off to the side just like a little chart that is taking derivatives. So as we move down this list, we are taking derivatives with respect to x. So it's just like a little chart off to the side, not actually in our notes. We're going to start with the sine of x. When you take the derivative of the sine of x, you get cosine x. Cosine's derivative is negative sine x. And then negative sine's derivative is negative cosine x. When you take the derivative of negative cosine x, you get negative sine, which is positive sine. So it looks like when you reach the bottom of this list, you just wrap back around to the top. So the derivative of negative cosine is that positive sign. But what we're learning today is antiderivatives, which is the opposite order of a derivative. So if moving downward in the list is taking derivatives, moving upward in the list would be taking integrals, again with respect to x. Okay, so this little function right here would be right in there between the integral sign and the dx. These signs are always bookends. I don't know if you've noticed, but we've got the integral sign first, and then our function, and then the dx on every single one of these problems. All right, let's fill out some stuff. We've got the integral of the cosine of x dx. So we start at cosine, and we just move up our list. Here we go. Integral of cosine x is sine x. Don't forget that little plus c at the end, because there could have been a constant that we take the derivative of to get 0. Over here, sine x. Sine x is at the top. Moving up the list, we got to wrap back around to the bottom. Negative cosine x. And then plus c. You better believe that as soon as I learned anything about sine x and cosine x and all those derivatives, when I learned how to make this chart, I put it at the top of every single test that I got for calculus as soon as I received that test. Because if you're in the middle of some kind of test and you're frustrated, confused, or whatever, and then you come across a sine and cosine problem, you can refer back to this instead of getting frustrated or maybe forgetting to put a negative sign. That's always a huge disappointment when you make a mistake because of a negative. Okay, first problem, we got the integral of 2 sine of x plus cosine x, one term at a time, just like when we're doing polynomials. Okay, so the integral of 2 sine of x is the same thing as 2 times the integral of sine of x. The integral of sine is negative cosine, so negative cosine of x, but then that 2 coefficient, we're just going to stick there. That's the same thing as 2 times negative cosine x, just looks a little bit neater this way. The integral of cosine of x is sine of x plus sine x, and of course, plus c. To the right, this guy is a mixture of polynomial and trig. Take the integral, t to the now third power. Oh, notice that these are t's, and then this became a dt to match. You'll see on a homework assignment that you've got thetas sometimes. As long as this is a d theta, you're good to go. Same process. Back to here. So that increased to a 3. This becomes a 1/3 in the front. Negative sine of t is here on the list, so its integral is going to be positive cosine of t plus c. So it looks like we always have one extra term that we did not have before, and it's the plus c. All right, next guy, 4x. The integral of 4x is x squared, and then 4 divided by 2 is 2. I'm going to go ahead and put that 3. Negative cosine x has an integral of negative sine x, and then plus c. Another thing I used to do on tests when I was in school is if I saw an integral sign, I would just put like a plus c on the answer blank at the end, because I knew that there was going to be a plus c and I was going to forget one. So that's a testing strategy. Okay, next guy, square root of x. All right, looks like we got to rewrite this guy. We are not currently taking an integral. We are doing a rewrite. That is x to the 1/2 power plus the sine of x dx. Now let's take an integral. This is going to be x to the, let's see, 1 plus 1/2 is 3/2. Then let's do some side work for the division. Dividing by fractions is just kind of annoying. So we start with a 1, and we are dividing by the fraction 3/2. 3/2 is going to flip over to be 2/3. It'll be 1 times 2/3, which is 2/3. And hopefully that makes sense. If you multiply an exponent of 3/2 times its reciprocal, it's all going to cancel out and become a 1. Sine x has an integral of negative cosine x, and then plus c. Okay, even though I've been doing these for a million years, my eyes keep flicking up to this list. Like, okay, if I'm starting with positive sine, where do I go? Negative cosine. All right. These next two problems are going to have the exact same steps in them, except just different numbers and different functions. So it's going to be the same process for both of these. Our goal on both of these problems is going to be to find f of x. So we are given the function f double prime of x equals 2, or f double prime of x equals x to the negative 3 halves. So given just that function, we can figure out f prime of x by taking an antiderivative, and then we can take the antiderivative of f prime to find f. I'm going to show you something. An integral or antiderivative of f prime of x dx is equal to, if you take the integral of a derivative, those guys cancel each other out. An integral removes one of those little marks. You get your original function back. Because the goal is to figure out what was the function where this is the derivative of it. If you take the derivative of this, you get the inside of this guy. All right, so we're going to be using this notation to help us write and set up our problems. Function, derivative inside of an integral. Okay, number 1, we've got f double prime of x equals 2. If we're starting with f double prime of x, and we take the antiderivative of it, the antiderivative is going to cancel out one of these little primes, which will leave us with f prime of x. This is a great place to start a problem because it helps you organize your work and it helps the person reading your work to know where you're starting. So this is what we're starting with. F prime of x equals, let's see, we don't know what f prime of x equals, but we do know f double prime of x is the function 2. Okay, I'm picking this function because it says f double prime of x, so we know it's a function, not this guy where it's f prime of 2. So the x on the input as opposed to a number on the input. That's how I know I have to start with this guy. All right, so f prime of x equals the integral of f double prime of x, which is the function that's just 2 dx. Okay, we know how to take that integral. We've got a constant. The integral of a constant is a linear term. F prime of x equals 2x, plus c. That's a problem. We don't know what c is. So off to the side, I'm going to put f prime of x equals 2x plus c. That's this exact same thing, right? It's just a little side work. We need to find c. We can use this part right here, f prime of 2 equals 5, to help us find that c. Because if x is 2, we can plug in a 2 right there. And then this would be f prime of 2. F prime of 2 is 5. 5 equals 2 times 2 plus c. 5 equals 4 plus c, which means that c has to equal 1. This c right here is 1. So I told you a while ago in this set of notes that sometimes we will be able to find c, and this is that extra information that they have to give us. If they don't give us that, our problem will still have c in the answer. All right. But we're not looking for f prime of x, we're looking for f of x. We know that f of x is the same thing as the integral of f prime of x dx. That's a thing that we just know. That is a rule. The antiderivative of a derivative is the original function, f. Okay, well now we know what our function f prime of x is. So f of x equals the integral of 2x plus 1 dx. We know how to take that integral. Notice that I'm rewriting that f of x all the way down that left side so I don't lose track of what I am finding. 2x is the derivative of x squared, 1 is the derivative of x, and then of course the plus 0, that is invisible, gives us a plus c. We need to find c. So I'm going to rewrite this off to the side. F of x equals x squared plus x plus c. And then we're going to use that last piece of information, f of 2 equals 10, because this is f. This one was f prime. So this gives us some information about if x is 2, f of 2, or f of x is 10. So 10 equals 2 squared plus 2 plus c. Doing a little PEMDAS over there on the right, we get 10 equals 4 plus 2, which is 6 plus c, which means that c must equal 4. Now you might be thinking, didn't c just equal 1 a second ago? These are different values of c. You're welcome to put like c sub 1 and c sub 2, like the little subscript, into your problem if you really want to. There's not a lot of point to it as long as you organize your work and you don't like mash it all together. Okay, our final answer for this is going to be f of x equals x squared plus x plus, and then instead of c, we're going to put a 4. This c actually does show up in our final answer, and c was 1. The antiderivative of 1 was 1x. If that had been a 5 or something, this would have been a 5x. So that's just kind of neat. They both do show up, just in different ways. Okay, second problem down here, same steps. So I will go ahead and work them out in the same way, same colors and everything. Let's start with f prime of x equals the integral of f double prime of x dx. It's just nice to have that set up. F prime of x equals the integral of x to the negative 3/2 dx. Nothing is happening to the left because there's no actions over here. We just know what this function equals. The action on the right is to take the integral with respect to x. This will become x to the negative 1/2, right? Increase negative 3/2 by 1, we get negative 1/2. And then we multiply times the reciprocal of this, right? Dividing by that exponent is multiplying by the reciprocal of that exponent. So 1 times negative 2 is negative 2. And of course, plus c. C1 if you liked that. Okay, off to the side, f prime of x equals negative 2. Okay, this right here is kind of ugly. So as I'm rewriting off to the side, I'm going to make this negative 2 over the square root of x plus c. And then when we plug in, it's so much easier to take a square root when it looks like a square root. Right? Our x value is a 4. Our f prime value is a 2. So 2 equals negative 2 over the square root of 4 plus c. Simplifying that fraction, square root of 4 is 2. Negative 2 over 2 is negative 1. So this is 2 equals negative 1 plus c. And adding 1 to both sides, we get 3 equals c. Okay, we plug that back in here for c. F prime of x equals negative 2, x to the negative 1/2 plus 3. Hopefully it's obvious that if that is a negative 3, you would put minus 3 here instead. So it's the same exact steps, just plug it in. It's a lot like a y-intercept. All right, keep going. We have f prime. Now we want to find f. F of x equals the integral of f prime of x dx. Okay. I did keep the negative 1/2 exponent instead of making it look like that square root over here because it is way easier to take an integral or a derivative, either one, when it's an exponent form. Okay, f of x still on the left equals, let's increase that exponent by 1. Negative 1/2 becomes positive 1/2. Okay, Then, since we are dividing by a fraction, really we are multiplying by the reciprocal of that fraction. Negative 2 times, flipped over, is a positive 2. Negative 2 times 2 is negative 4. Plus 3x plus good old c. We got to find c. So f of x equals negative 4 times the square root of x plus 3x plus c. We are told that f of 0 equals 0. That guy is our favorite because that means we get to plug in 0 for x and 0 for f of x. 0 equals negative 4 times the square root of 0 plus 3 times 0 plus c. A little bit of simplifying there. 0 equals 0 plus c, which means c equals 0. Now you might be thinking to yourself, why did I have to go through all of that effort if I can just figure out that c equals 0? And that's because when you take the AP exam or the College Now exam or my exams or a final or whatever, if you don't put plus c and then solve for c, you don't earn all of the points. It's not that you get points taken away, you're just not earning the points that are available to you. So I think it's worth 2 points usually on these types of problems to put the plus c and solve for it and then substitute it back in. So f of x equals negative 4 times the square root of x plus 3x. And then of course it is a plus 0, so you would just stop here. But if you skip this stuff, you just lose out on 2 points that would have been available to you for very little effort. Next page, we've got an evergreen nursery. A plant nursery takes baby plants called seedlings and cares for them as they grow for a certain number of years and shapes them so that they look nice and they're more likely to survive. During those 6 years, the growth rate is approximated by this thing called a differential equation. A differential equation has a differential, which is just this thing that looks like a fraction. It's the dHdt business. Okay, so this is a derivative function or derivative equation. Remember, we use the word differentiate. That's the same thing, differential, differentiate. Here it is. So this guy right here is the derivative with respect to t of the function h. That all means the same thing. H prime of t is the same thing as dH dt. Okay, where t is the time in years and h is the height in centimeters. We could figure out a label for this right now based off of this fraction looking thing, right? H is in the, air quoting this because it's not an actual fraction. It's in the numerator. So h is height in centimeters. This would be centimeters per, and then t, the time in the denominator, is in years. So this is centimeters per year. If we were to plug in a number for t and simplify that out, this would be the rate in centimeters per year. Okay. This also means that after every year, or every second really, every day, every month, whatever, of time that has passed, the rate is going to change. So this should feel a little bit like a related rates problem, except there's only one rate, not a second one. All right, the seedlings are 12 centimeters tall when planted at t equals 0. So this is h equals 12 when t equals 0. We can rewrite that as h of 0 equals 12, right? Our t value is 0 when our h value is 12. Okay, so that's really all the information they give us, except that the shrub is sold after 6 years of growth and shaping, so we will probably come back to that 6 at some point. Okay, letter A, find the value of the differential equation above, this guy, when t equals 3. Let's start there. So h prime of 3 equals 1.5 times 3 plus 5, which is 4.5 plus 5, 9.5 centimeters per year. Using correct units of measure, check. Explain what this value represents in the context of the problem. So this is going to feel like one of our related rates sentences. We usually start with those with like at, and then we say a certain time. So often that derivative is with respect to time. At t equals 3 years, or after t equals 3 years, something like that, then what is the thing that is changing? The height is changing. The height of the shrub and we have to decide, is that shrub's height increasing or decreasing? Because the rate's positive, it is increasing. It is increasing at a rate of then 9.5 centimeters per year. Done. B, find an equation for h of t, the height of the shrubs at any year t. Then determine how tall the shrubs are when they are sold. So we're looking for h of t when we are given h prime of t, right? H prime of t. We know that h of t is the integral of h prime of t dt, right? Integral or antiderivative of a derivative is the original function. Now I keep saying original function. I mean the thing that's not the derivative. It's not the rate. Okay. We know the function for h prime of t, so let's plug that in there. H of t equals the integral of 1.5 t plus 5 dt. We're going to increase our exponent by 1. Actually, I'm going to change that 1 or 1.5 to 3 over 2. I'm going to make that into a fraction. 1.5 is the same thing as 3 over 2 because fractions are easier to deal with than decimals when you're dividing. All right, t to the second power, and then 3 halves divided by 2 is 3/4. Okay, you could also think about multiplying by the reciprocal of 2, which is 1/2. So 3 halves times 1/2 is 3/4. Plus 5t plus c. Can't forget that regular old plus c. So we probably need to figure out what c is. Let's do it. H of t at a certain t. So we're looking for like h of something equals something. We found that over here. The seedlings are 12 centimeters tall. That's a height at t equals 0. So everywhere we see a t, we're going to put a 0. Everywhere we see h of t, we're going to put 12. 12 equals 3/4 times 0 plus 0 plus c. Love that good old 0. Zeros are really our, like when t equals 0 or x equals 0, that's really a y-intercept, a starting value or a y-intercept. So 12 equals c. That's going to be this guy right here. Okay, let's do our rewrite. H of t equals 3/4 t squared plus 5t plus 12. That is the first thing we were supposed to do, find the equation for h of t. Then determine how tall the shrubs are when they are sold. These shrubs are sold when they are 6 years old. So everywhere we see a t, we're going to put a 6. We got h of 6 equals 3/4 times 36. So that'd be 3 times 9 is 27. Plus 5 times 6 is 30. Plus 12. We will also need a label when we're done with this. This is h is a height, and a height is in centimeters for this problem. So h of 6 equals 69 centimeters. These are the two things we were asked for. Got 2 problems left. Has to do with velocity and acceleration and position. A particle moves along the x-axis, so just like the back and forth line with this velocity. We can rewrite this. We know we're going to have to anyway, so let's do it now. V of t equals t to the negative 1/2 power. T is greater than 0 because we're not going backwards in time. And we know at t equals 1, position is 4. So this is going to be one of those extra pieces of information that helps us take our integral and find c. So we probably need to rewrite this as a something of something equals something. This is a position function. Usually those are labeled with an s. So like s of t equals a number. So the position equals 4 when t equals 1. S of 1 equals 4. Fantastic. Okay, A asks for acceleration and B asks for position. So we are probably going to need the position, velocity, and acceleration functions. Okay, off to the side, I'm gonna rotate this and then just take a little bit of notes in a margin. If we start with a position function and we take its derivative, we get a velocity function. If we take the derivative of a velocity function, we get the acceleration function. So moving down the list here is derivatives, probably with t, yep. And moving up the list is going to be our integrals. Okay. As we take integrals, don't forget your plus c's that you're going to have. So here we started with velocity, and in part A, we're asked for acceleration. So we are taking one derivative to get there. In part B, we're asked for position, and we've got velocity. So we are going to take one integral to get from velocity to position. That's our plan. Okay, over here in part A, what is the acceleration of the particle when t equals 9? So if v of t equals t to the 1/2 power, v prime of t, which is a of t, is 1/2 t. Oh, whoa. That's a negative. I copied it wrong. My bad. Negative. So negative 1/2 t to the negative 3/2 power. Let's do a quick rewrite of that. This is going to equal negative 1/2. T to a 1/2 power would be a square root of t. And then the 3 exponent means you are cubing. You're allowed to cube the t on the inside or on the outside. But since we are plugging in a number that's a perfect square, we're plugging in a number that's a perfect square, which is 9. It's going to be easier to take the square root of 9 and then cube it. Make it small and then make it bigger. And this equals a of t. So a of 9 equals negative 1/2 times the square root of 9 cubed. The square root of 9 is 3. You can, of course, at this point, plug it all in your calculator. It's not like super pretty to do. You have to pay attention to what's in the numerator and denominator very, very carefully. 3 cubed is 27, and 27 times 2 is 54. So you can leave it like this for the acceleration, or you can do something else. Make it a decimal. I don't care. It'll be like negative 0.19 or something. 0.019. We are not given any labels, so we cannot label this. Next problem, position of the particle when t equals 9. So if we're starting out with v of t, to get s of t, we would have to take the integral with respect to t. S of t equals the integral of t to the negative 1/2 dt, and I think we've done this exact thing before. S of t equals t to the positive 1/2. Flip that fraction over and multiply it times 1, we get 2 plus c. We know, this is kind of our side work, we know that if t is 1, then s of t is 4. So this is 2 times the square root of 1 plus c. This is 4 equals 2 plus c, which means c equals 2. We can rewrite s of t. Rewrite s of t as 2 times the square root of t plus 2. Now we're asked to find when t is 9, what is the position? That's s of 9 equals 2 times the square root of 9 plus 2. 2 times 3 is 6. 6 plus 2 is 8. So s of 9 equals 8. Done.